So today we're going to be looking at a few different topics. One is sort of reviewing amphiprotic compounds, what we refer to as conjugate acid-base pairs, and the difference between strong and weak acids and bases. So it's going to be a multiple of different things. I'll try to keep it kind of flowing in that order though. So before we go into that, I want to just review this new way of looking at acids and bases. Under the Bronsted-Lowry definition, it deviates from the Arrhenius definition in that an acid is classified as a chemical that can donate a proton or donate something that was H pluses. So just you're giving an H to another compound. And the thing that takes the H, takes the proton, is the base. So in this illustration here, we can see that HA is our acid, and it's giving the H to the base B. So we can see this transfer of the hydrogen to the base B. And then on the protic side, you can now see that you're left with A minus and HB plus. And so that would be the effect of that acid-base interaction. Now the system is in equilibrium, these equilibrium arrows here. And that sort of implies that the reaction could go backwards. And we see that A minus is reacting with HB plus, and the A minus takes the H. So the A minus would take the H and go back into HA. And you have this sort of back and forth movement. So notice on one side there's an acid and a base. So on the left side there's this acid and this base. But on the right side, there's also an acid and a base. So this is the acid, and this is the base. And that does differentiate Bronsted-Lowry from Arrhenius also. Generally, in an Arrhenius reaction, when you mix an acid and a base together, you get salt and water. And that's a pretty common theme taught in grade 11 chemistry. But in Bronsted-Lowry reactions, you actually, when you react an acid and a base, you get an acid and a base. So that's quite different than maybe how you would have thought of it last year. Okay, so now there's this word conjugate here, which I will talk about a bit later. But here's a specific example we can look at. And here's the reaction between sulfuric acid and water. And you might remember last day we said that water is a strange compound because it can act as an acid and it can also act as a base. But it's not saying it's acidic or basic. Water actually is always considered to be a neutral compound, but in the Bronsted-Lowry definition, it sometimes has the ability to take protons, and sometimes it has the ability to give up protons. So in this example, water is reacting with an acid, so it would kind of make sense that if you're reacting it with an acid, then it would have to be a base, because acids by definition give protons. So sulfuric acid, H2SO4, is able to give one proton to the water. That's what that arrow represents. And just sketch that in there. So that's that arrow there. Lots of arrows here. And so that's giving the H to the water. And the water now turns into this new compound we talked about last day called hydronium. So the hydronium ion. And that is the result of water taking a proton from an acid. On the right-hand side of the reaction, though, we can see the sulfuric acid is turned into bisulfite ion. And that ion now has one less proton than sulfuric acid had. And so if the reaction was to go backwards, it would be the bisulfite ion that would take the proton from the hydronium. So this would give one of its H's back to there. And that would form into sulfuric acid. And that means that the bisulfite ion, this ion right here, is actually acting as a base. Whereas the hydronium ion would be acting as an acid. It would be giving the proton to bisulfate. So it's kind of confusing, kind of goes back and forth. Now, not all reactions are equilibrium, but many of the ones we're going to study will be equilibrium reactions. We'll talk about how you know when it's going to be equilibrium and when it may not be equilibrium. So amphiprotic compounds, that's our big talk for today, is a compound that can act as an acid or a base. And so it has the ability to do both. And what we really want to know is what makes it amphiprotic. How do you know as a student that a compound is amphiprotic? What characteristics could you look for that would tell you that? So here's an example of an amphiprotic ion, and this is the bicarbonate ion. If you're a bi-12 student, you've probably seen this quite a bit with respiration and the circulatory system. But we're looking at purely from the point of view of it being amphiprotic. So if bicarbonate ion was to act as a base, it would have to be able to take a proton, and if it took a proton, it would turn into H2CO3, which is carbonic acid. And so that would be it acting as a base. So it's taking a proton. That's the definition of bases. The right-hand arrow shows bicarbonate ion acting as an acid, so it's losing a proton. So if you took the proton away, it would turn into CO3 2-, which is carbonate. And so that would be the chemical acting, bicarbonate ion, this ion here, that would be acting as a base if it did that. As an acid, I'm sorry. So this would be it acting as an acid, and this on this side would be it acting as a base. So if the compound can do both things, then it's considered to be amphiprotic. Many compounds are not amphiprotic, and we'll take a look at the distinction between those. So so why would it be amphiprotic, I guess? Well, I guess one thing you could consider is that if something's to be an acid, what does it have to be able to do under this new definition? Well, the definition of Branch-Lowry is that to be an acid, you have to donate a proton. So what would you have to have in the structure to be able to donate a proton? Like, what would you be looking for as a student? Well, in order to donate a proton, you'd have to have hydrogen. So you have to have H's present. So a compound like, let's say CO3 2-, that compound, there's no way that could act as an acid because there's no hydrogen available to give up. So this could not be an acid. So that cannot be acidic. Now, a compound like the example we just gave, HCO3-, that does have a proton right there, has an H. So this could be acidic. It's possible to donate that proton. So this can be acidic. So what about to be a base, though? Let's say we were looking at something and considering it to be basic in nature. Well, in order to be a base under this new definition, you have to be able to take H. So if you're something that can take something that's positive, what would be beneficial that you maybe are? Like what would make something like a H+ move towards you in solution? Well, you might guess that an opposite charge would be a good candidate for that. So generally, if you have negative charge, then you would most likely be able to accept the proton. Now, it's not always the case, and we'll show you the exceptions to this later. But generally, if you have an H and you have a negative charge, then good chances are you could be amphiprotic. So obviously, HCO3- has an H and has a negative charge, which makes it a good candidate to being amphiprotic, the ability to take protons and to give up protons. So does an amphiprotic compound do both? Like, is it an acid and a base simultaneously, or is it just sort of an acid in one situation and a base in another situation? And that's a bit of a difficult question, but I'll give you an example quickly here about this. Let's say you had a compound like HF, hydrofluoric acid, and you were reacting it with the bicarbonate ion. Well, HF is an acid. Like we know that's an acid, and so we know that acids donate protons, which means in this case the bicarbonate ion has to be a what? If HF is going to donate its proton, then bicarbonate would have to by default be the base. And the products here, once again, pause the video, see what you think you would get here. So the products here would be fluoride, because the H would have been removed from that. Oh my goodness, I'm getting a phone call.